Have you got a notice that I'm recording? Yeah, okay, great. All right, so a bit of a small crowd today, but sometimes people come late and we've just started the recording so we can share it. So I'll begin the introduction for today's speaker. This is the One World seminar series on the mathematics of climate. And we monthly invite someone to talk to us about new methods and techniques for understanding climate from a mathematical perspective. I'm really pleased today to introduce Hao Fu, Dr. Hao Fu, who is currently a T.C. Chamberlain postdoctoral fellow in the Department of Geophysical Sciences at the University of Chicago. He recently finished his PhD at Stanford. Actually, he's my first graduate. He's my student, and I learned quite a lot from him. So it's an honor to have him speak and share his latest work, which I haven't seen. He did his undergraduate at Nanjing University, and he was also last year a fellow at the Woods Hole GFD summer school. And he's an expert in convective dynamics and tropical meteorology and tropical cyclogenesis. So I'll give the floor to Hao. Hao, thanks so much for joining us. We really appreciate it. And we'll take questions at the end. So unless anyone has a very urgent clarifying question, please hold it to the end and then we could have a discussion. Thanks very much. Go ahead.
Thank you, Morgan, and thank you everyone for coming. As an early career scientist, it is my real pleasure to study at a forum that combines both climate and the mathematical sciences. Actually, I'm not a mathematician. I'm still learning a lot of math. And today, actually, yeah, I'm going to talk about a topic which I started at the University of Chicago in collaboration with Professor Da Yang, and on the synchronization of convective life cycles. So my talk will be mostly about relatively new phenomenon we identified and how we model it with theory and finally got an analytical solution. And actually half of the seminar will be some literature review. So I hope you guys will enjoy what is the beautiful nature of tropical convection and what are the possible mathematical tools or physics ideas we can use to approach them. Okay, so before saying too much, let's go into the topic. So we know that atmospheric motion have a lot of timescales. For convection, on the order of 1 hour, we have cloud, and but on the order of 1 day or so, we will have some cloud clusters, and for over a year, we will have the intertropical convergence zone. So they all interplay in our climate system. However, climate system is not just about cloud. They're also about a lot other processes, such as the gravity waves, which is relatively fast, and the diurnal cycle, and the seasonal cycle. So a very critical question, both for modeling and also for prediction, is how the convection interact with those other processes. So here is the outline of my talk. I will first make a brief introduction to the convective life cycle, and then answer or make a review and try to answer a very challenging question, that is, how does a cloud population respond to external forcing? And then I will provide some evidence of convective synchronization in a cloud permitting simulation, which I found synchronization might be a unique way for cloud population to respond to external forcing. And finally, I will present a simple model of convective synchronization. Okay, let's go to some very basic but also very interesting thing about what is convection and what is the atmospheric vertical structure. We usually have a convective boundary layer, which is relatively unstable for the lowest 1 kilometer of our atmosphere. And we have around 10 kilometer deep free troposphere, which is stable to dry convection. However, we have water vapor, and the release of latent heat in the phase change from vapor to liquid water will provide extra buoyancy that will drive some moist convection. Above, there is a very stable stratosphere where hardly any convection can penetrate through. And now let's make a very brief review of how does a cloud form. We usually first have moisture accumulate in the boundary layer. And once the air parcels can ascend somehow, they will cool by adiabatic expansion process. And this cooling will cause the condensation that turns water vapor to liquid water and release latent heat. This provides extra buoyancy that can make parcels soar into the sky, building the beautiful cloud tower. And once the cloud parcels are in the sky, there will be cloud droplets. The cloud droplets are really tiny things, and they can grow larger to form raindrops. So how do they grow? First, they usually have a random collision coalescence of small droplets, which aggregate to larger ones. Then, the collection of small droplets by larger droplets will lead to raindrops, which grows larger and larger. And those raindrops will finally fall to the boundary layer. And once they experience some evaporation at the subcloud layer, because the subcloud layer is still not saturated, they will evaporate. They will produce cooling and will drive a downdraft. So in summary, we use this classic cartoon from the textbook of Markovsky. That is, we first have a towering cumulus stage, and then the material convection stage where precipitation is produced from the cloud, and finally the dissipation stage where the downdraft cut off the updraft. So we summarize that moisture and heat in the boundary layer first accumulate and then get released. That makes convection generally intermittent. So we hardly see a convection that sustained for a very long time unless there is a vertical shear or the air column gets saturated. For example, in the hurricane eye wall, that's something much more complicated, which we will not mention. Okay, so after having a look at the individual cloud, let's look at a cloud ensemble, which loosely denotes a collection of a large number of clouds. I want to understand cloud ensemble by drawing an analogy to the definition of fluid parcel. So this should be large enough to accommodate enough number of clouds and therefore reach a statistical, make any statistical property significant. However, it should also be small enough to make the background gradient sufficiently smooth. For example, as shown in this white square, it should be much larger than individual clouds, but it shouldn't be as large as the whole tropics, because otherwise there will be a lot of gradient inside, and it's hard to say this cloud ensemble represents anything specific. So there is an implicit assumption carried between them, that is the scale separation between the individual cloud scale and the scale of the background gradient, for example, the tropical whites. Okay, so let's watch a simulation movie to get a sense of what is a cloud ensemble. So this is a large eddy simulation I performed using Brine Cloud Model 1. It has a uniform sea surface temperature, no Coriolis faults. The surface color, the color will be the near surface water mixing ratio. And you will also see some gray surface that visualize a cloud liquid water, cloud boundary, basically. So you will see the clouds first gradually grow from shallow to deep as the simulation starts, and then reach a quasi-equilibrium state. You see, those clouds never, evolve for so long time. They will die and produce a dry air pool, which is called actually also a cold temperature region. It's called cold pool. And when the cold pool collide with each other, they will trigger some new convection. So in this back and forth process, the clouds evolve in a quasi-equilibrium state. And we call the collection of all these clouds cloud ensemble. Okay, so then let's talk about the physics of cloud ensemble. The most direct one is energy balance. So from this is a very classic cartoon from Arakawa and Schubert. So we see a cloud ensemble has clouds of various size at different stages of their life cycle. First, they will outgoing long-wave radiation that radiatively cool down the atmosphere to make them convectively unstable. And that will be compensated by the latent heat release of the cloud, and therefore produce a rough radiative convective equilibrium state. And the balance seems to be simple, but probably more difficult question is how does a cloud ensemble respond to external forcing? That is, if an equilibrium system we give it a kick on it, what will it respond? What is the timescale of response? So I will first review some previous findings from a step changing like forcing, and the other is from the periodic step forcing to see what previous studies have already tell us. First, when the forcing is step changing, this classic paper by Cohen and Gregg provides some insights. So what they do is they suddenly change the radiative cooling at some point. So break the radiative convective equilibrium state and investigate how does the low-level convective mass flux respond. So convective mass flux basically denotes the updraft mass that goes through the cloud, a measure of the convective activity. There will be, after the forcing, the step changing forcing is imposed, there will be first a short adjustment timescale of an hour, which they found to be the time for gravity wave to propagate the cloud spacing. So basically how one cloud feels the response and then transfer it to another cloud. However, there will be a much longer adjustment timescale for about 10 days. So these 10 days are needed for the moist static energy to be vertically transported, or in other words, for moisture to adjust, because moisture is generally a tracer that can only slowly advect rather than like buoyancy, which can propagate out like gravity wave, which is very fast. And that's for the step changing. And they found that probably this is just like a linear relaxation process. And, by linear, we mean that it obeys a superposition principle. That is, a different strengths of forcing will have, their response timescale is not sensitive to that. Okay, then let's go to the oscillatory forcing, which looks more mysterious. So this paper by Davis et al. Studies departures from convective equilibrium with a rapidly varying surface forcing. Their surface forcing is a surface heating, which includes both the sensible and latent heat. So this is the forcing scheme they prescribe. They first make it at a relatively constant state, and then start the periodic, behavior. And they studied roughly 3 scenarios. When the forcing period is relatively slow or too slow, then in this case, convection is just subordinate to the forcing. That is, adjust to the forcing in the quasi-equilibrium state. So it seems that when there is forcing, there's convection. When there's no forcing, there's no convection. The second experiment they make is when the forcing period is too short. It's really, really fast. Then in this case, you can see the convection is relatively continuous, although there are still some oscillation, which is the imprint of the forcing. So in this case, convection hardly feels the forcing. They will just evolve mostly in their own way. So what about a scenario between them? That is, when the forcing period is between 3 to 12 hours, they did a series of experiments and I found that the convective amplitude actually varies from cycle to cycle. You can see that there is a mysterious wave packet-like feature here, which is a little bit hard to interpret. And if we just look at the first few, cycles, we may want to speculate, oh, is that could be a resonance or somehow? This is just my own speculation. Just want to show you that this is a relatively complicated response behavior. And then we come to some theoretical understanding, which actually comes before those numerical study. That is by Penn and Randall. They study cumulus parameterization with a prognostic closure. And so they regard deep convection as a recharge-discharge cycle. So what is recharge and what is discharge? The A here is the energy variable. That is, we call a cloud work function. So it is the convective available potential energy that considers entrainment dilution. So you can just understand it as some energy that is accumulated to drive convection. And then, we have another equation that governs the convective kinetic energy. And that is something that is driven by the energy. That converts from the, with potential energy to kinetic energy. And then the model needs to a closure. That is, how does the convective kinetic energy, depends on the cloud-based mass flux. And this closure can be argued to be semi-empirical. And although they use some argument to defend that. And but combining all these things, there will be a very mysterious result. That is, especially in the case of damping free, that is, the tau d comes to infinitely large, they will get a linear oscillator equation to describe this recharge-discharge cycle. Well, this is a very impressive finding. But however, later on, people argue that why do you give this simple semi-empirical closure? We did obey a more universal scaling like the power of p. And in this case, you will get a nonlinear oscillator. Things are not that elegant. And so it provides some, uncertainty and criticism. And later on, people also based on numerical simulation to propose some predator-prey type model, which greatly advanced our understanding of the cloud ensemble evolution. So you can see that people try to make some physical argument, but if they just stare at the cloud ensemble, it is hard to dig deeper, and we have to invoke some semi-empirical closure to complete this problem. So what should we do to go a little bit further? And here comes our idea. Possibly people focus too much, maybe on the microscopic property, but what about let's give a connection between the microscopic and the macroscopic behavior? And that is possibly a missing piece, the synchronization of individual climactic life cycle. So basically, the life cycle of a single cloud is not necessarily the same as the life cycle of the cloud ensemble. We need to study them possibly separately. So synchronization is an interesting concept, but we are certainly not the first people to devise this concept and apply it to atmospheric convection. The only paper we know that applies this thinking is by Fingal and Corin in their paper, A Model of Coupled Oscillators Applied to the Aerosol Cloud Precipitation System. They propose a self-synchronization model for shallow convection. So by shallow convection, I mean those mesoscale cellular convection, which is frequently seen in the mid-latitude and subtropical oceans, where though they don't develop pretty deep, only maybe 3 kilometers deep, and they can behave as a closed cell or open cell, like the Rayleigh-Bénard convection, which is really beautiful. And here is a simulation from Corin Fingart's paper Supplemental Material. And you can see that those vertical velocity pattern will have like some periodic behavior. And so they want to explain it. So the model they propose have three governing variables: the cloud top height, droplet concentration, and rainfall rate. So you can see that they're all based on microphysics. And because they consider especially the aerosol to play an important role in the cloud deepening process. And so they assume that the neighboring clouds are assumed to couple via the boundary layer convergent and divergent flow. And there will be a delayed function to depict the neighboring cloud's influence on this cloud. And the system, after they produce some simulation, which is numerical integration of their simple model, the system self-synchronizes when the coupling strength parameter takes a moderate value. That means it's not too small or not too large. And I would say this is a very impressive model with the strength that they demonstrate the adjustment of phase, period, and amplitude, and when they interact with each other. However, I have to say that there might be some limitations. In my opinion, it's still a little bit semi-empirical, but at the same time, it's hard to solve analytically. We still need to rely on the numerical integration. They have a lot of regimes, which is very interesting, but I think it still looks to me a little bit complicated. And also, they are mostly for the mesoscale cellular convection. It's not quite the same as the tropical convection, which we focus on. So so I would say this is a very, very impressive model, which I learned a lot from. But we still want to try to build another model and to be more suitable for tropical convection. Yeah, so here, before building a model, let's do some cloud permitting simulation to get a sense of what is going on. And we are still, again, using the Brine Cloud Model 1 and the uniform sea surface temperature, no Coriolis force, W periodic domain. And we will observe some convectively coupled gravity waves that grow spontaneously. So I would first make you cautious that these waves are probably not that realistic in the real atmosphere, because we found that it really depends on the domain waves. If you make the domain a little bit larger, the wavelengths will grow a little bit larger with the domain waves. But if we make it very, very large, we found that it indeed have its unique, length scale. But anyway, so our focus is not on the dynamics of the wave, but just use this simple setup, the wave in this simple setup as a forcing to study how the cloud ensemble respond. And we will leave future, more investigation on what on earth those waves are for future work. And I would say that even if this setup is a little bit unrealistic, but there might be possibly it turns out to be an advantage. That is, the wavelength is constrained by the domain size. That means we will have a controllable large-scale forcing. Yeah. So here is our simulation result. With the quantity we look at is called outgoing long wave radiation. It is measures where there's cloud and where there's no clouds. When the OLR is relatively large, that means the long wave radiation directly radiates from the surface. So that means it's a clear sky region. And when it's a blue, which means the outgoing long wave radiation is relatively small, that means it's a cloudy region. And because cloud top is relatively cold with a low brightness temperature. So on the right panel is the whole domain. On the left panel is just we zoom into it to see whether we can see more structure. So at the beginning, convection is relatively random. Oh, I'm sorry. Probably the simulation figure movie is a little bit large, so the PowerPoint is may go through a restart. But yeah, just wait a second. It will be okay, I think. Yeah, don't worry. Yeah, let's restart from this figure. So basically, you will see that at the early stage, it is relatively random. But if we go to the late stage, you will see as the wave develops, the cloud is also seems to be synchronized. Like you see there are like knowing each other. I think they know each other and they go up and go down at almost the same time. And this is a very interesting feature which we want to study. And so because all outgoing long radiation is a relatively, we use it because it's easy to obtain. For example, either from you can from the model output or it's close to the satellite observations, brightness, temperature, but we still need a variable that can tell the physics a little bit more closely. So we choose the equivalent potential temperature. So it's called theta E. So theta E is a conserved variable in vapor liquid phase change. And if we look at the thermodynamic equation, we can easily see that it is conserved under the water phase change. And we particularly focus on the theta E vertically averaged in the boundary layer because that have been shown by previous work to represent the convective potential. By the boundary layer, we mean both the mixed layer, which is lowest 600 meters, and the entrainment zone, where the boundary it is a transition region between the free troposphere and the mixed layer, with also a lot of moisture residing there. Okay, so with this in mind, and we will just let it be, assume it to be a key variable of convective life cycle and further analyze the result. So the reason why we focus on theta is because it will influence the convective inhibition energy and the convective available potential energy. So what is the convective inhibition energy? It is shown in this blue shading region. It is the mechanical work needed for a surface parcel to ascend to a level that is more buoyant than the environment. In other words, we all know that a parcel can release its latent heat and finally goes up to the tropopause. But the latent heat release is not undergone at the very beginning. It still has to go to the first to the level lifting condensation level. And at this level, the latent heat release is relatively small, so it's still not buoyant enough. So there has to be some external forcing that can lift it upwards a little bit until it is more buoyant in the environment. Then it can spontaneously grow and release its energy. So after it reaches the level of free convection, which is the intersection between these two lines, the cape will release. And so I found a very nice illustration of Thin and Cape from the cartoon of Brian Mapes' 1997 review paper. And they consider the convection as a small ball that is rolling on a rigid surface. And before they can release their convective available potential energy or simply release their potential energy, they have to overcome a barrier, and that is the convective inhibition. And once it goes to the upper point, it will roll down and release the energy and possibly go through another cycle. And so here are the key concept of sin and cape. And then I found actually in my simulation, the equivalent potential temperature is generally in phase with cape and in anti-phase with sin, which means when the equivalent potential temperature is relatively high, it will say cape is relatively large. And but at the same time, that means convective inhibition is almost eliminated because now the parcels is really have a lot of energy and moisture, and so it won't spend a lot of energy to overcome convective inhibition. And and actually, by the way, sin and cape also depends on the free troposphere buoyancy, and it's not just the parcels quantity. So this figure just shows that possibly in this setup, the parcels equivalent potential temperature can roughly determine sin and cape. But we also make it conservative that the free troposphere also have an influence on that. Just a note for you. Yeah, so with that, we will introduce a core screening analysis. That is basically a multi-scale analysis and of the equivalent potential temperature. The first step is to find the most oscillatory quarter of the domain and basically define our cloud ensemble. Because you see our domain is that large, but they are at different phase of the gravity wave. For example, here we have convective phase. The other part is just at the dry phase. So as remember, we want a cloud ensemble to be a region where the background property is relatively uniform. We don't want to include too much background inhomogeneity. So we have to choose either it is at the peak region of convection or it's at the valley region. And that means we need to choose a quarter. And the second step is to split the quarter into 20 kilometer by 20 kilometer cells. And each cell represents a cloud and its code pool. That means it is wider than an individual cloud, which is only 2 kilometers or 3 kilometers wide, but the code pool is relatively wide. So we view them as an entity. Okay, so here comes our simulation. And the left figure is just the normal equivalent potential temperature without doing anything in this quarter. But on the right is the core screen analysis, which means we are averaging them in a 20 kilometer by 20 kilometer cells and appear like the mosaic pattern. You will see that the mosaic pattern is good at identifying the activity of those convection, especially at the late stage, where you see they become synchronized, and that is a block of bright part and the block of blue part, and so that means now we can further analyze the synchronization with this mosaic pattern. Okay, so here comes the first a little bit core part of our research. That is the amplitude decomposition algorithm of the cloud ensemble. So you can see that this blue line is actually an averaged equivalent potential temperature in this quarter, and which already contains the information of many clouds in the cloud ensemble. But we want to decode it into the information of individual clouds. That means how does the individual clouds contribute to this cloud ensemble? So I randomly chose around 10 trajectories of individual cell, and to show that at the beginning they just have fluctuations at their own way, and but because they are at random phase, so the ensemble average doesn't show anything. But at the late stage, you will see that there are both the growth of individual clouds amplitude and there seems to be some synchronization of their phase, which both contribute to the growth of the ensemble average quantity. So how to decode those ensemble average into the contribution of synchronization and the contribution from individual clouds growth? So first, I will let's define what is the ensemble to identify the cloud ensemble average amplitude. You don't need to look at this equation, and I'll just sketch the idea for you. So what I do is I first put a window and I calculate the standard deviation of quantity within this window, and then make it smoothly grow and go and go, so I can record the standard deviation at each step. And you can certainly see it will be something that's going up, which I will show in the next slide. So this is for identifying the cloud ensemble average amplitude, which is a moving average of the standard deviations, which is quite simple. Then, and we need to look at the individual cloud's amplitude. And this is a little bit more complicated because you see, individual cloud have their own amplitude, and each of them are quite different from each other. So we couldn't just randomly pick one and repeat the operation and say, okay, this is the individual cloud's amplitude. We have to do an average. So what we do is we will go through each member and calculate their standard deviation, and then make an average of their standard deviation, and so that this standard deviation will represent the an average quantity of all our members. And then we will repeat this step for the next time step and make an average, and then another one. So this is basically how we identify individual cloud's amplitude. And for the synchronization, and it's something a little bit, the equation is more complicated, but I will just show you the basic idea. That is, I will consider that is a 1 minus the variation in space over the spatial temperature variation. Because the synchronization is something measures how different clouds are at the same phase. If there is no variation between them, that means they are all the same, then that means they are synchronized. So that's why I use the variation in space as a measure. The higher the variation in space, the lower the synchronization index. But you don't actually need to be too concerned about why I don't give an equation. Actually, I found with some derivation that with this definition, it is actually the ensemble average amplitude divided by the individual convection's amplitude. That means the ensemble average amplitude is actually contributed by the synchronization index times the individual convective amplitude. So that accomplished the decomposition of the cloud ensemble's amplitude into each cloud's growth and their synchronization. So I'll show you the result. The upper figure is the same as the one I just showed, but with a different aspect ratio. And the second one, the blue line, will show the growth of the individual cloud. So you can see they indeed double their amplitude as the wave grows. And however, the ensemble average, which is shown in the blue line, the red line, grows from a very small value and all the way up. And the synchronization index diagonals from it is a quantity between 0 and 1. 0 means it's not synchronized at all, and 1 means it's fully synchronized. So you can see the synchronization will grow. And this dashed black line shows the product of individual amplitude and the synchronization index, and which actually turns out to match well and with the ensemble average. So this validates the robustness of this amplitude decomposition. And this amplitude decomposition can be applied to any data, I believe. So I think this might be a useful method you guys may want to use, and I'm happy to share the code with you. Yeah, so just want to emphasize that the growth of ensemble average is due to both the growth of individual clouds and the synchronization. And then let's look at the synchronization by building a very simple convective life cycle model. So just we are trying just to bring our most basic understanding of a recharge discharge cycle of convection, which I introduced at the very beginning, using the equivalent potential temperature in the boundary layer as a variable, just one variable. First, it will grow up in the shallow stage. By shallow stage, I mean it's mostly shallow convection and congested convection because the energy in the boundary layer is still not very high. It's not sufficiently high to support any deep convection. And then at a point when thin is generally eliminated, it will transition to the deep stage, where the deep stage comprises of deep convection and stratiform precipitation. Stratiform precipitation means basically consists of the remnants of deep convection, because the deep convection transport a lot of moisture to the upper troposphere without enough time, to precipitate out. So they have to precipitate in the form of stratiform clouds, and that's what's called the stratiform precipitation. And then after the deep convection, because deep convection will consume the convective available potential energy and reduce the equivalent potential temperature in the boundary layer until a point where even CAPE is exhausted. So that means thin and CAPE holds two bonds. And when they overcome thin, it transitions from shallow to deep. And when the cake is exhausted, it will transition from deep to shallow. And so basically, if I write out the governing equation, it will compress of just a few terms. The first term is radiative cooling term, which I diagnosed and use budget analysis to find that it is a generally negative constant quantity, which is cooled down the boundary layer. And we have a surface heating effect, which is a positive constant quantity because surface flux have a lot of energy, from the sea surface to the boundary layer. And however, the more interesting thing is the convective transport, which I set as a piecewise constant negative quantity. Here, the transport is negative because the convection is like a mechanical stirring effect that is always thrusting some dry air to the boundary layer and transport some moist air out of it. Even for shallow convection, it is still, drying the boundary layer. But it is just more negative at the deep stage because deep convection have a higher level of the air partial source, so bring more very low theta E air into the boundary layer. And we also have a wave forcing term here, and which is the vertical advection of background equivalent potential temperature. And so if I summarize in summary, this is a very special type of it's an oscillator. It is nonlinear in that it is controlled by two threshold processes. And another interesting thing is it has a fixed amplitude. That means even if the amplitude wants to grow higher, it will trigger the threshold and make it go down. So it has to be trapped between a lower and upper threshold. However, what we can change is its phase. That means the arrival time for example, from shallow convection to deep convection, and that will change the phase of the cloud, and therefore make some adjustment, which I can show you. Okay, so here is a simulation result by a numerical integration of the model. So the red line is the wave forcing, which is just a very simple sinusoidal function, which I prescribed. And the light blue ones are the individual clouds equivalent potential temperature in the boundary layer. I mean, the cloud means the cell, which includes both itself and the cold pool. And you can see that at the beginning, I set in random phase. As a result, their ensemble average quantity, which is shown in the deep blue line, is just do not change very much. However, as the time goes, there is some synchronization behavior, and that makes the ensemble average growth actually like a sinusoidal wave, which is a very interesting phenomenon. And at the late stage, where most clouds complete their synchronization, and they will, you see, even the ensemble average will appear like a tent function. So that means the synchronization is saturated. Yeah. And then we compare that with the cloud. So before comparing, we noticed that the ensemble average is in phase with the forcing and with the forcing's vertical velocity, I mean. And this feature actually also appear in the cloud permitting simulation, where the vertical velocity in the boundary layer is in phase with the average equivalent potential temperature in the boundary layer. So although, yeah, we would say this is the most direct support of our model from the simulation, cloud permitting simulation perspective. But in some after slides, I will show that we couldn't predict the growth rate very well because we found there are a lot of complicated processes can influence the growth rate. So we will just use this phase relation as a direct validation or kind of limited validation to our model to just let you know that it's the limitation of the model. Okay, then comes to the exciting part, that is, how does the phase adjust? Why is this such a simple model can carry the synchronization behavior? So let's look at this diagram, with the horizontal axis is the time. The red line is the wave forcing, and the blue line is the unperturbed convective phase, which appear as a tent function. Go to the upper threshold, and go to the lower threshold, and goes up, goes down. And the yellow line is the accumulated wave effect. So by accumulation, I mean, let's just focus on the deep convection state where the tent function is going down. And so the yellow line is actually the integral of the red line along this area. Because we all know when we study calculus, we use shading area to represent integral, right? And so in this case, you see the yellow shading the positive and negative area cancel each other, which means the wave's acceleration and deceleration effect on the convective life cycle almost cancels out. So the convection cannot feel too much the wave, and therefore it is a relatively stable locked state. Oh, by the way, I forgot to mention, I have to prescribe the wave and the convection has the same frequency. That means they have the same period. This is also a significant limitation of our model and to study the synchronization, because we still haven't come up with how, if we have a different frequencies and how the adjustment will occur. So this just leave as a question for you. And then let's study a next case, that is when convection lags the wave. So in this case, what I mean by lag, that means you can see the wave comes to its peak earlier than the convection. So I say convection is lagging the wave. And in this case, the yellow area will be mostly negative. So that means the wave is trying to push down the theta e in the boundary layer, and therefore makes the blue line deviate to the green line. That makes it will descend faster than otherwise. And that will happen to make the convection wave closer in phase, and therefore, adjust the convective phase to the wave phase. And the similar is true if the convection leads the wave, which I will not analyze any deeper. So the general idea is that we can see that due to the two threshold effect, the wave synchronizes the convective life cycle by modulating its phase and adjust it to a locked state. Yeah, so here is a cartoon diagram. And then we will briefly, I know time is limited, we'll just briefly go through the mathematical part of what is the relation between an individual cloud phase to a cloud ensemble's amplitude. And by phase, we have defined that when it's at the bottom, it's phi is 0. When it's at the top, the phi is at the pi. And then it goes to 2 pi and then so on. And the first step is to derive the phase drift rate of individual cloud, of each cloud, and which appears like a relaxation equation, but you notice a sinusoidal function here. And the second step is to derive the phase distribution function rho, because now we need to not just look at individual cloud, but look at what all clouds behave like in the histogram, essentially to make a prognostic equation of how their histogram evolve. And finally, we can use the histogram to solve the ensemble average, because we know at different part of the histogram, they have different theta e. So there's a relationship between them. So we can solve the equivalent potential temperature, I mean the average one, from the histogram. And finally, use the solution to analyze and found that actually the ensemble average equation obeys an oscillator equation in an approximate sense. And this is a very interesting result. And this 8 over pi square factor is something related to the shape of the tent function, and which is something very, very interesting. And so in other way, the phase adjustment of individual cloud turns out to be some oscillation equation of the cloud ensemble that is building a bridge between the individual cloud and the cloud ensemble. And then let's make some benchmark of this model. And before that, let me first review that the restoring mechanism of this oscillator is the transition between the shallow and deep stages, which is constrained by the elimination of convective inhibition and the exhaustance of K. And we have to make 4 assumptions in deriving the model, which may not make sense to you in this presentation, but it should be important to emphasize. First, the shallow and deep stage duration times equal each other. This is mostly just a mathematical convenience, because we haven't worked out the case where they are not equal to each other. So we can't say much about if they are not equal to each other. And the second is the wave Folsom period is not far from the convective life cycle period. And so even if the mechanism we just talked about also for this simulation also only shows the case where the wave and the convection frequency equal each other, but actually this oscillator equation can work for a case where there are frequencies are different. So we do not need this assumption, but we don't want them to be too far from each other. That will break down some assumptions in deriving the model. In the third case is the wave forcing must be relatively weak. and also the synchronization status is weak, which basically means we only focus on the small amplitude case where the synchronization is weak. So these are just the limitations of the derivation of how we arrive this oscillator, which I hope you will know the limitations. Yeah, and here is a benchmark simulation where I tried a different frequency ratio between the wave and convection. You can see that only when the ratio is the same, it will be like a resonant solution where the amplitude will grow linearly with time. And if they deviate from each other, and then we will only have a wave packet which cannot really grow. And also you notice there's a difference between the simulation and analytical solution as the frequency becomes more and more deviate from each other. So that means the oscillator is not a perfect result. It is an approximation under the four assumptions which I have shown you. Yeah, so by this time, we have derived an oscillator, but we may remember that Tan and Randall also got an oscillator in my literature review. And their derivation is mostly based on the cloud work function A, kinetic energy, and the cloud-based mass flux. So they are directly studying the energetics of the cloud ensemble without looking at individual cloud, and then obtain this beautiful oscillator equation. So I would say that possibly we are just obtaining possibly the same result, but from different angles. Our angle is from the individual cloud, and then study their synchronization. But Pan and Randall's idea is from the energetics by only looking at the macroscopic stuff. And so I couldn't confirm that they are equivalent to each other. But I would say that's possibly an analogy that is obtaining the same result but from different angles, which is quite interesting. And we can also add some noise to the model because I just mentioned that our model actually cannot predict the growth rate of the convective ensemble very well compared to the cloud permitting simulation because there are a couple of complicating factors that are influencing the synchronization rate. I'll just make one example that is adding noise. So in this is just an old figure which there's no noise. But if we add some noise, as you see from this wiggling part of the convective trajectory, you will see the synchronization still occurs, but it's much slower than before. And we also don't know how strong is the noise. So that means we just couldn't make this model very predictive at this moment. So the noise suppresses synchronization by disturbing the phase adjustment. And we also hypothesized that can this noise be parameterized as a damping effect in the oscillator equation, probably something like this. It's just a question which we found interesting but haven't confirmed yet. Okay, so time flies. So we are at the end of my presentation. So I'll give a brief summary. So we first point out there's a outstanding question in the community, that is the response of the cloud ensemble to periodic external forcing is really something not well understood. But a lot of previous studies have provided very inspirational work, which we build upon them. And we first analyzed the cloud permitting simulation and then proposed an algorithm to diagnose the synchronization index simply by decomposing the amplitude of the cloud ensemble due to the amplitude of the individual cloud and the synchronization process. And we found that the phase synchronization of individual clouds and actually will modulate the amplitude growth of the cloud ensemble due to the synchronization. And then we proposed a nonlinear convective life cycle model with two thresholds, which we argue to be related to the sin and the k. We found cloud ensemble will approximately obey a harmonic oscillator, echo with the work of Pan and Randall. And yeah, so by the end of this talk, I want to summarize that our idea is to link the cognitive life cycle and the cloud ensemble, and which many previous people have also tried, and we are just adding our tiny contribution to this giant plaza. And maybe it is kind of similar to the flavor in physics. That is, when we study the thermodynamics, people usually start understanding a phenomenon from its macroscopic thing. That is the thermodynamics. For example, we can define pressure, volume, temperature of a system, and then study their relation. For example, we found the ideal gas law, and with some measurement, and which is a seminal progress in physics. However, if we want to explain the physics law discovered from thermodynamics, we have to go to statistical mechanics. and all the way to the gas kinetics, how what is the ensemble behave, and what is the distribution function. We have Boltzmann distribution, we have a lot of things, and partition function, a lot of stuff. And so this might be analogous to the connective life cycle. That means to go in, our understanding of the convection may start from the ensemble, but we finally need to go to the individual cloud level, which will finally enrich our understanding of the cloud ensemble. So I think this is just a very small analogy with the statistical physics, which Junichi Yano have a nice review paper in 2012, and also Maxime Collin, which is an early career scientist, have also some idea on how to link the microscopic and macroscopic part. So we hope that that you guys are probably mathematicians, and this is a very interesting field, and I really think it is deserves paying more attention to the convection and apply your expertise in math and physics to address those questions which are really pressing for predicting climate change. Yeah, and thank you very much. And here are people I really indebted for. First is George Bryan and NCAR, who devised this Bryan Cloud Model 1. And the second is the Boulder Summer School of Condensed Matter Physics. It happened at 2012, happened a few years ago, where I got this idea and inspiration, where Yuhai to give a lecture on the synchronization of biochemical clocks and propose and talk about the Kuramoto model, and also helpful comments from Bolei Yang, Chris Li, Zhihong Tan, Jack Gladys, and Morgan, Yongqiang Sun, and Zhao Huawu, and they really pointed out a lot of limitations of the model and are really in depth. And thanks for watching. And here is my email. And please feel free to send me any messages or criticism, and I'll be happy to learn from you. Thank you.
Thanks very much, Hao. That was a terrific and clear talk. So I'd
Thank
like to
you.
open the floor for questions from our audience. If you'd like, you can just unmute yourself. You can also put something in the chat, but you're welcome to just unmute and go ahead. Any questions for Hao? Maybe while people gather their thoughts, I have a quick one. Could you put noise in the frequency of your wave ensemble?
Ah, that's a terrific question. And yeah, I read some papers that, for example, study mechanical oscillations, they will do so. And so in my current model, the noise is simply just the
Yeah, it's
right-hand side
outside.
terms. And
Right.
if we want to put noise, I would say first, the oscillator model is the outcome of this microscopic model. So what we can do
Mm.
is we can only add noise at this microscopic level and then
Okay.
study what the oscillator looks like. I think your question might be, could the noise, for example, if it's like this, appear as a noise here? And in the oscillator
Yeah,
equation,
yeah,
will that be the case? Because that will make the frequency deviate and possibly break down
right.
the resonance. Certainly, I don't know the answer, but this
Okay.
is a great idea because I suppose it could be a linear damping effect. But as you
Hmm.
thought, maybe there's also something here, and so yeah, I don't know. And
Right. Yeah.
yeah, thank you for your question.
Yeah, for sure. Do we have other questions from the audience? Oh, we have a chat question. How do you think your results will compare with GCM simulations? Can any comparison be made?
Oh, that's also a very important question because any simple model, ultimately, they should be compared to GCM or the observational data. So I would say, first, what we can do, because my contribution, this talk mainly talk about two things. One is the amplitude decomposition algorithm. The other is a model. So I would say for the amplitude decomposition algorithm, it can certainly be applied, although I haven't done so because so long as you have some data like this, the two-dimensional data in space and time, then you can use this algorithm to diagnose it, and which we can try. But for the theory part, I would say it is difficult, but we will finally do that. I want to mention one thing about the resonance hypothesis, or which is something in this shown in this equation. actually many papers have hypothesis that there are convection wave resonant with gravity waves, analyzing their cloud permitting simulations. And however, for example, Breston 2006, Lane and Fu Qingzhang, Todd Lane and Fu Qingzhang, Da Yang, and maybe Bolei Yang, and also a couple of people. And however, the difficulty is how to confirm the resonance. And it's super difficult because resonance is a physical process. You couldn't say there's a periodic behavior. Oh, that's resonance, or it's amplifying. That's resonance. Oh, that's not the case because that could be simply due to other processes. So I would say this is something we must be very cautious about. But I think the synchronization might be a unique path to confirm resonance if there happens to be. Because right when we say resonance, we are only analyzing the cloud ensemble averaged quantity. So we will just look at the time series, which is a one-dimensional data. But synchronization is actually something deeper. You get more information from different clouds. So I would say maybe to confirm there's a resonance, the first step is to confirm there's a synchronization. And so I still need to think about the relationship between synchronization and resonance, whether it's a sufficient and necessary condition, or probably just one way, or probably none. I don't know. So it's a great question, I would say. I don't know.
Any other quick last minute questions? They also ask, has this amplitude decomposition method been applied to study convective organization as opposed to convective self-aggregation?
Ah, great question. So first, convective organization and self-regulation are different concepts. And because organization could be a regular pattern, which do not need to be clustered together. But aggregation usually means there's just one cluster or one or two clusters in the domain. And yes, so I will show you a linkage to self-aggregation that is in my backup slide. So what about we make the domain a little bit larger? And what will the wave do? So here are three simulations with just different domain weights. And what we are looking at is the outgoing long wave radiation. This is similar to our simulation I reported. You will see that those will be some waves, and those waves seems to trigger a convective self-aggregation. And you see the simulation only takes 7 days. And in this left figure, there's nothing happened, just wave growing. But when the domain is large enough, the wave amplitude seems to be much larger. And also, I don't know whether that is due to the domain or so. There are some like a standing wave. And that means there are some wave node region and wave anti-node region. That makes things inhomogeneous. And that may finally cause a self-aggregation, maybe something like this. And but I think we still need to make further research, especially using a large domain simulation. And this is something my small domain simulation didn't do very well. And that means wave may trigger self-aggregation. But what about the synchronization directed aggregation? That is something more, a little bit more distant. I'll keep that in mind. Thank you. Yeah.
All right. That's all the time we have for questions. I'm going to stop the recording. Stop recording.